All right, welcome to Did You Just Feel That? A lesson on earthquakes. My name is Blair Schneider and I am the outreach manager for the Kansas Geological Survey.
I'm Layla Joyce. I am a graduate research assistant at the Kansas Geologic Survey.
And so today we are going to talk to you about earthquakes. And we have 5 major learning goals. First, we want to understand what an earthquake is, identify where earthquakes can occur, and then we're going to give you 2 case studies, a first case study from earthquakes here in Kansas, and then a second case study looking at the earthquakes in Puerto Rico. And lastly, of course, we're going to teach you what to do if you're in an earthquake. So let's begin. So what is an earthquake? It's a sudden and violent shaking of the ground as a result of movements within the Earth's crust or volcanic action. This movement releases stress, which is energy that's been built up by forces inside the Earth. And so if you watch this animation here, maybe, no, there it is. Our earthquake occurs and it sends these acoustic waves through the interior of the Earth, which creates shaking along the ground. And so here's another animation that kind of gives you an example of how that earthquake occurs. Here we're at a plate boundary. So we have one plate that is subducting below the other. I'll go ahead and hit play. And these plates are moving. So they have the oceanic plate subducting below the continental plate, and there's an area where they get locked. So the plates are still moving, but there's an area here where they're actually stuck together, and it's really building up stress. And eventually that lock is going to release, as you see here, and an earthquake occurs. The strength of that earthquake depends entirely on the amount of stress that was released at the time. And another important thing I want to point out about this is if you look at the time frame here, it's taking hundreds of years for that stress to build up. And then when that earthquake actually happens, it's all happening within about a 30-minute time frame, or maybe an hour. Yeah, making the slides change. So where do earthquakes occur? This is a snapshot from Smithsonian Mag, so definitely check them out. It's a really cool resource. Earthquakes, 98% of our earthquakes correspond to our plate boundaries. And so this image that you're looking at here on the left is a map of plate boundaries across the globe. And this image here, again, taken from Smithsonian Mag, is showing you green dots that represent an earthquake of magnitude 4 or greater since approximately 1898. And so each of these green dots here, you can see pretty much perfect little outlines following these plate boundaries. But so if 98% of our earthquakes occur on plate boundaries, 2% of them have to occur somewhere else. So how do we have earthquakes in the central United States? So what I'm showing you here is actually a hazard map that was created by the USGS, the United States Geological Survey. And it shows the probability that ground shaking will exceed a certain level over a 50-year period. The low hazard areas indicated in gray and blue have a 2% chance of exceeding a designated low level of shaking. And high hazard areas, which are more of that red purple color, have a 2% chance of topping a much greater level, much more damage at the surface. So here in Kansas, we're kind of relatively pretty much contained within this blue area of hazard level, which is a low level of hazard. But nearby in central US, we have this really hot spot area where we have some high hazard. So we're gonna look at both of these areas to understand why we're having earthquakes there, since we don't exist on a plate boundary in this area. So this hotspot area is known as the New MADRID seismic zone. And it's really well known because in the winter of 1811 and 1812, it generated a sequence of earthquakes that lasted for several months and included 3 very large earthquakes estimated to be between a magnitude 7 and 8. They destroyed several sediments along the Mississippi River, caused minor structural damage as far away as Cincinnati, Ohio, and St. Louis, Missouri. And they were felt as far away as Hartford, Connecticut, Charleston, South Carolina, and New Orleans. In this region, it also dramatically affected the landscape. They caused bank failures along the Mississippi River, landslides in Kentucky and Tennessee, and uplift and subsidence of large tracts of land in the Mississippi River floodplain. At one point, actually, there's a particular area where it actually forced the Mississippi River to flow backwards. That's how extreme these earthquakes were. They liquefied subsurface sediment over a large area, resulting in ground fissuring and violent venting of water and sediment. One account of this phenomena stated that the Pemisco Bayou blew up for a distance of nearly 50 miles. So this is a pretty popular area because we've had some pretty big quakes hit, and so they're wondering what's going on. So beginning in 1974, we installed, the USGS has installed seismometers. These are instruments that actually measure the ground shaking. And they've recorded thousands of small to moderate earthquakes in northeastern Arkansas, southwestern Kentucky, southeastern Missouri, and northwestern Tennessee. And that's what's indicated on this map here. So what's happening here? So the seismic zone here is about 45 miles wide and about 125 miles long. And what we're dealing with here, so the seismic zone is located in the northern part of what has been called the Mississippi embayment. That's what you're seeing here at the surface. The upper 30 meters of sediment within this embayment is just sand, silts, and clays deposited by the rivers and their tributaries over the past 60,000 years. And then just below that, you've got a layer of marine sedimentary rocks that are about 50 to 100 million years old. Below those marine rocks, we have some rocks that are Paleozoic in age. They're sedimentary, and they're 570 million years old. Below those, the rocks are even older, and we have evidence that about 600 million years ago, these rocks became deformed because 600 million years ago, the North American continent almost broke apart. And during this process of continental rifting, there was a deep valley that formed, and it's bounded by faults. It's known as the Reelfoot Rift, and so that's that buried rift here. Today, we can identify this as a subsurface system of fractures and faults in the Earth's crusts. So that's what the geology looks like below this region. And so then there's multiple hypotheses as to why we have so much seismic activity here. These include fracturing in this region is resulting from stresses brought on by the downcutting of the Mississippi River into the landscape. They claim that the erosion of surface material in the region allows the upward force of warmer expanding rocks below to overcome the weight of the remaining rocks above. Other hypotheses attribute faulting to the continued rise of the crust stemming from the most recent ice age. So after those glaciers actually melted and retreated back, that what will naturally happen is the continent will actually start to like rebound or uplift because that weight has been removed. And then the buildup of pressure within that Reelfoot Rift zone located in those crustal rocks underground also creates changes and could be contributing to the faulting and fracture zone here. So the faults on which the earthquakes occur here are buried beneath 100 to 200 feet thick layers of soft river sediments called alluvium. So we actually can't see them at the surface, and that makes it harder to observe and harder to track. So it leaves a lot of unknown questions, and that's why we have multiple hypotheses to try and explain this question. So how do we have earthquakes in Kansas? So again, 2% of our earthquakes generally don't occur along the plate boundaries, and these are called intraplate earthquakes. And they're produced when rocks beneath the Earth's surface suddenly move along faults, which are just fractures that occur at weak points in the Earth. Geological processes such as the deposition and erosion of surface rock can actually trigger faults by altering the balance of stresses on these subsurface rocks. So just natural processes can trigger these faults and create stress that builds up and then releases. In Kansas, we actually do have a few structures that can create natural earthquakes. So the first one that you'll see here is the Nemaha Ridge, indicated in blue here. It runs north to south across Kansas and extends into Oklahoma and into Nebraska. It's a buried mountain range. It was formed about 300 million years ago and is bounded by faults that are still slightly active today, especially the Humboldt fault zone that forms the eastern boundary of the Nemaha Ridge. About 50 miles west of the Nemaha Ridge is the Mid-Continent Rift, and that's a zone, so that's indicated by green here, a zone of the Earth's continental crust that was ripped apart and filled with oceanic crust, so basaltic rock, about 1.1 billion years ago. This zone of rifting extended from central Kansas near Salina, northeastward across Nebraska, Iowa, Minnesota, and all the way up into the Lake Superior region. We don't know why, but the rifting stopped after spreading only about 30 to 50 miles. And if it hadn't stopped, eastern and western Kansas would likely be on different continents today. Kind of a cool fact there. But so these areas, the Mid-Continent Rift, the Nemaha Ridge Zone, and then the central Kansas uplift zone here, are areas where we have seen natural earthquakes occur. And so here's kind of a summary of the history of earthquakes in Kansas. We do have at least 25 documented earthquakes, and by that I mean we have 25 instances where people like noticeably felt an earthquake in the state between 1867 and 1976. So to better understand earthquakes in Kansas, seismologists at the KGS actually maintained a network of seismometers throughout the state beginning in 1977 through June 1989. This network could pick up ground movements 1,000 times smaller than the thickness of a human hair. So for example, they could detect artillery firings at Fort Riley from 30 miles away. And they could also register large earthquakes from locations as distant as Japan and South America. So during these 12 years of recording, they recorded more than 200 small earthquakes in Kansas and Nebraska. The largest one measured a magnitude 4, and the smallest was a magnitude of about 0.8. And so that largest one recorded was centered near Wamego, which is east of Manhattan. Oh, excuse me. The largest recorded Kansas earthquake was centered near Wamego, east of Manhattan, all the way back in 1867. So this was not during their recording over this 12-year period. It measured a 7 on the modified Mercalli scale and toppled chimneys, cracked foundations, and was felt as far away as Iowa. So we do have earthquakes in Kansas. They have gotten up into the 4 and 5 range, even more recently. But the level of damage isn't what you would see on like a plate boundary. And Layla's going to be talking about that during her portion of the presentation. So while we do see damage from earthquakes in Kansas, it's a lot different than the type of earthquake you would experience if you were in Puerto Rico or in California on one of these major plate tectonic boundaries. So we have another contributor for earthquakes in Kansas, and that's something called induced seismicity. So beginning in 2013, the state saw an increase in seismic activity, particularly in the south central part of the state. This increased shaking raised questions about whether human activity or induced seismicity was to blame. And so one of our solutions to study that was to install another seismic network. And so we actually have one of our scientists here, Shelby Petery, installing one of these seismic network stations out in western or south central Kansas. And here's a map showing you where our seismic network stations are across the state. We currently have 12 in these different counties, and we are planning to install 6 more. So in the years 2013 to 2014, nearly all of the recent earthquakes occurred within 2 southern counties. So what you're looking at here, Harper and Sumner County down here is where we were seeing a large chunk of these earthquakes in that time frame. And so what you're looking at on this map here, the dark dots show the locations of earthquakes reported by the USGS and the KGS from between 1977 through 2012. The orange dots indicate earthquakes reported by the USGS in 2013 and 2014. And the light green areas are showing you some of those prominent subsurface geological structures, okay? And so what we were looking at here is when we're dealing with induced seismicity, or when we're thinking about induced seismicity, we're looking at industry production. So we're looking specifically at Class 1 and Class 2 wells. Currently, the state manages 50 Class 1 wells, and so these are deep industrial wastewater wells. So any wastewater or kind of waste products can be injected into these deep wastewater wells, which are managed by the Kansas Department of Health and Environment. And then across the state, we have approximately 5,000 saltwater disposal wells. These are called Class 2 wells. And these are managed by the KCC. Cumulative injection volumes in most areas of the state have been consistent for the past several years, but there was a dramatic change in approved volume increases occurring in central and south central Kansas, where Harper and Sumner are. And so when I'm talking about well injection, just to clarify that really fast, and what you're looking at here is actually a picture where they inject materials into a well. Extraction of oil and gas from underground produces really large volumes of highly saline water. And so this water, after it's extracted, is then typically disposed of in deep saltwater disposal wells. And we're talking thousands of feet below the surface. And so during this time frame, the annual saltwater disposal volume in Harper County increased from the historic rate of about 10 million barrels to more than 100 million barrels by 2015. So this is a huge increase. This is a 3 to 4 times increase compared to historic levels and what they're injecting into. Most of these high volume wells inject fluid into a rock formation called the Arbuckle Group, which is made up of highly permeable Cambrian to Ordovician age sedimentary rocks. There's no underlying confining layer in many places with this unit. And so these rocks are hydraulically linked to the Precambrian granite basement that lies below. These basement rocks typically have many faults that are both we've either mapped or we don't know about. And generally they have sparse historical earthquake activity. So that's the key thing here. Large injection rates that are now coming into contact with Precambrian granite basement below. So in response to that, we did have a regulatory response after discovering this. The KCC ordered reduced injection volumes for saltwater disposal wells located within a set of ellipses defined around these high seismicity zones in Harper and Sumner counties. So you can see right here, these black ellipses here, those are those high seismicity zones where they ordered reduced rates. So by July 2015, saltwater disposal rates were reduced to near the maximum historic rate in the area prior to this uptick in earthquakes. A year after saltwater disposal volumes were restricted, earthquake activity within this injection restricted footprint dropped dramatically. We only had about 250 earthquakes of magnitude 2 or larger in 2016 compared to nearly 800 in 2015. And so here you're seeing those earthquakes after these injections were reduced, and you can see a real drop in the number of earthquakes that have occurred. Now, one thing I do want to point out, we have a really common misconception that induced seismicity is because of hydraulic fracturing, often called fracking. That really isn't accurate, and so I want to make sure we address that misconception here. So to be clear, the first frac job in Kansas was actually all the way back in 1947. We have been hydraulically fracturing wells since 1947, but this induced seismicity issue wasn't raised until 2013. So historically, fracturing of wells has been going on for a long time, but this induced seismicity is just now becoming more prominent. So I'm going to play a video for you. This is done by Marathon Oil, and I think it does a really good job of explaining what happens when a well is hydraulically fractured from start to stop.
Geologists have known for years that substantial deposits of oil and natural gas are trapped in deep shale formations. These shale reservoirs were created tens of millions of years ago. Around the world today, with modern horizontal drilling techniques and hydraulic fracturing, the trapped oil and natural gas in these shale reservoirs is being safely and efficiently produced, gathered, and distributed to customers. Let's look at the drilling and completion process of a typical oil and natural gas well. Shale reservoirs are usually 1 mile or more below the surface, well below any underground source of drinking water, which is typically no more than 300 to 1,000 feet below the surface. Additionally, steel pipes, called casing, cemented in place, provide a multi-layered barrier to protect freshwater aquifers. During the past 60 years, the oil and gas industry has conducted fracture stimulations in over 1 million wells worldwide. The initial steps are the same as for any conventional well. A hole is drilled straight down using freshwater-based fluids, which cools the drill bit, carries the rock cuttings back to the surface, and stabilizes the wall of the wellbore. Once the hole extends below the deepest freshwater aquifer, the drill pipe is removed and replaced with steel pipe, called surface casing. Next, cement is pumped down the casing. When it reaches the bottom, it is pumped down and then back up between the casing and the borehole wall, creating an impermeable additional protective barrier between the wellbore and any freshwater sources. In some cases, depending on the geology of the area and the depth of the well, additional casing sections may be run and, like surface casing, are then cemented in place to ensure no movement of fluids or gas between those layers and the groundwater sources. What makes drilling for hydrocarbons in a shale formation unique is the necessity to drill horizontally. Vertical drilling continues to a depth called the kickoff point. This is where the wellbore begins curving to become horizontal. One of the advantages of horizontal drilling is that it's possible to drill several wells from only one drilling pad, minimizing the impact to the surface environment. When the targeted distance is reached, the drill pipe is removed, and additional steel casing is inserted through the full length of the wellbore. Once again, the casing is cemented in place. For some horizontal developments, new technology in the form of sliding sleeves and mechanical isolation devices replace cement in the creation of isolations along the wellbore. Once the drilling is finished and the final casing has been installed, the drilling rig is removed and preparations are made for the next steps, well completion. The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume, and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins. Initially water and then natural gas or oil flows into the horizontal casing and up the wellbore. In the course of initial production of the well, approximately 15 to 50% of the fracturing fluid is recovered. This fluid is either recycled to be used on other fracturing operations or safely disposed of according to government regulations. The whole process of developing a well typically takes from 3 to 5 months, a few weeks to prepare the site, 4 to 6 weeks to drill the well, and then 1 to 3 months of completion activities, which includes 1 to 7 days of stimulation.
So I'll just kind of pause it there. So you can kind of see with that hydraulic fracturing, the amount of that explosive, I would compare that to, when they set that off, that charge at that kind of a depth, That's like equivalent to maybe like dropping a gallon of milk on the ground. So that activity is not what's contributing to the induced seismicity in Kansas. What we are seeing is that they said when they pulled that plug, the first thing that comes out is water. Here we go, get that, there we go. So the water that they pull out, so the Groundwater Protection Council estimates that US oil and gas industry generates approximately 3,400 billion liters of produced water each year. So before the oil and gas comes out, all of that salt water or that brine water is actually extracted from these wells, and it has to go back underground. So if they are injecting this groundwater, this wastewater into these disposal wells, and they're doing it at too high of an injection rate, it can trigger underlying faults within the subsurface. And I wanted to show you a really cool resource that you have to play with. You can actually explore Kansas earthquakes. If you visit the KGS website at the following link, you can look at different earthquakes across the state or in particular counties. You can look at them by year. You can, so right here, any earthquake that occurred over a magnitude 2 is indicated for the year of 2016. This would be a great way to kind of explore and play with what's happening across the state. So I'm going to kind of go through here. Here's in 2017, all earthquakes over magnitude 2, 2018, 2019. So, you know, look and see what patterns or trends are you seeing occurring over time. All right, before we move on to Layla's case study, let's quickly talk about an earthquake in Kansas. What do I do during an earthquake in Kansas? There's a really cool resource called Shakeout, and I'll include the links to these safety video series so you can watch them. But essentially, stop, drop, and cover. If you have an earthquake occurring and you're inside, you need to stop, drop, and cover. Let's make these move on. So if you're indoors, stay there. Get under a desk or table and hang on to it. Or move into a hallway or against an inside wall. Stay clear of windows, fireplaces, or heavy furniture, appliances, or things that can fall on you. Get out of the kitchen. That's actually a really dangerous place. And don't run downstairs or rush outside while the building is shaking or while there's danger of falling and hurting yourself. If you're outside, get into the open. Get away from the buildings, power lines, chimneys, and anything else that might fall on you. And then what about when you're driving a car? If you're driving, stop, but carefully. Move your car as far out of traffic as possible. Don't stop on or under a bridge or overpass or under trees, light posts, power lines, again, anything that could fall on top of your car. And then stay inside your car until the shaking stops. And I recommend, you know, stopping, putting your emergency brake on. When you do resume driving, make sure to watch for breaks in the pavement, fallen rocks, or any other bumps in the road. And then lastly, if you're in a mountainous area, I know we're in Kansas, that's not quite the case, but you know, for traveling, you do need to make sure to also watch out for falling rock, landslide, trees, and other debris that could be loosened by quakes. All right, we're now going to transition over to Layla.
Okay. Can you see my screen now?
Yes.
Okay, great.
I'll mute myself.
All right. All right, I'm ready whenever.
Go for it.
On December 28th, 2019, Puerto Rico began experiencing a swarm or series of strong, shallow earthquakes. The first, at magnitude 4.7, shook the south coast of the island and was felt to some degree across much of the territory. Over the next week, even stronger earthquakes would rock the island, causing power outages and leaving thousands of people homeless. To understand why those earthquakes occurred, let's look at Puerto Rico's tectonic setting. This slide shows the tectonic plates that influence the earthquakes in Puerto Rico and the rest of the Caribbean. So we see the North American plate, the South American plate, the Cocos plate, and the Caribbean plate kind of squeezed between them. The arrows indicate the direction that the plates are moving, and the red and yellow dots show earthquake epicenters. You can see that they definitely occur along a lot of those plate boundaries. So just to help you get yourself kind of oriented as to where we're talking about, here's the Yucatan Peninsula of Mexico. Here's Cuba, Hispaniola, the island that holds both Haiti and the Dominican Republic, the island of Jamaica, and then under this cloud of red and yellow dots is the island of Puerto Rico. And the smaller islands of the Caribbean kind of curve down here under this cloud of dots. So let's zoom in a little bit to look a little bit more closely. So now we're looking at the northern boundary between the Caribbean plate and the North American plate. You can see that rather than being just one line, the boundary between the plates is more of a zone. There are several microplates. You can see these three here. Several microplates that are squeezed between the two larger plates. In some places, like north of Puerto Rico and south of Puerto Rico, so north of Puerto Rico and south of Puerto Rico, the plates are being subducted, or one is being pulled underneath the other. Then in other places, like here to the north in the Dominican Republic and Haiti, the plates are kind of grinding past each other. So think about people walking past each other in a really tight crowd. As you might imagine, being squeezed between two larger plates puts stress and strain on the microplate that contains Puerto Rico and the US Virgin Islands, which are right here. So if we zoom in even further, we can see what that strain looks like in terms of fault zones within Puerto Rico. So here we see the island of Puerto Rico and the fault zones that run through it. So this map only shows where the fault zones appear on land, but it's important to remember that those fault zones do extend down under the ocean. So we have the Great Northern Puerto Rico Fault Zone, the Great Southern Puerto Rico Fault Zone, and then down here, the Northern Boquerón Bay Punta Montalva Fault Zone. So as before, each of these dots represents an earthquake epicenter of degreeing magnitudes and locations. So based on what I've told you so far, you might think that Puerto Rico is no stranger to earthquakes. And you're sort of right. Puerto Rico frequently experiences earthquakes, but they're either too small for people to feel or just a slight annoyance. Before this year, our last big earthquake occurred over 100 years ago in 1918. So on October 11th, 1918, a magnitude 7.3 earthquake struck northwest Puerto Rico and was felt strongly across the entire island. The earthquake triggered a landslide under the ocean in the passage between Puerto Rico and the Dominican Republic, which then caused a tsunami. So within 10 minutes of feeling the earthquake, the sea pulled back from the shore, exposing coral reefs and leaving fish gasping on the sand. Then a 20-foot wave rushed onto the northwest and west coast. The earthquake and tsunami killed 116 people, destroyed homes, businesses, and small farms that lay near the coast. Aftershocks of the earthquake would continue for over 6 months. So here we see several buildings that have been destroyed by the shaking itself. These are brick buildings. So all of these photos are actually from my hometown of Mayaguez on the west coast of Puerto Rico. These other images here, here, and here are homes and businesses that have been literally pulled out to sea by the tsunami. So the epicenter of the 1918 earthquake was just about up here to the northwest of Puerto Rico, so about where that cursor is. And it reverberated down the Great Southern Puerto Rico Fault Zone. Our current strong earthquakes, or our most recent strong earthquakes, have their epicenters off the southwest coast down here and reverberate along this northern Boquerón Bay Punta Montalva fault zone. The first earthquake, a magnitude 4.7, was felt on December 28th of 2019. A magnitude 5.8 followed on January 6th of 2020. Then, early in the morning on January 7th, a magnitude 6.4 shook everyone awake. This is ATM security footage of the moment that the earthquake struck. So you'll see the man run towards his car to kind of hold on to it, and it's because his young daughter was inside the car. So the three strongest earthquakes on December 28th, January 6th, and 7th were accompanied by many, many aftershocks. Schools, homes, historic churches, and geologic features, which you can see here on this slide, collapsed. Thousands of people lost their homes, and many more feared sleeping in their homes because they didn't know if it was safe. People slept in their cars, in tents, in makeshift refuges, and out in the open if they had to, if they had no other choice. We were also afraid that there would be a tsunami. Thankfully, there wasn't. It's important to note that part of the reason the 2020 earthquakes were felt so strongly and were so devastating to infrastructure is because the epicenters were very shallow. An epicenter of intermediate depth occurs at approximately 87 kilometers below the surface of the Earth. The 2020 Puerto Rico earthquakes, the epicenters were only between 1 and 3 kilometers below the surface. The earthquakes were so shallow that people could sometimes hear the waves moving through the rocks below them. It was really very frightening. Today, Puerto Rico continues to experience small aftershocks. The aftershocks will probably continue for months to come. But even when the aftershocks stop, the legacy of these earthquakes will continue. Satellite imagery showed up to 7 inches of displacement due to the earthquakes. In practical terms, this means the areas closest to the epicenters are now nearly 7 inches lower in elevation and shifted very slightly to the west. So this image is from NASA. It was created by NASA and from satellite data, and it shows how much displacement or change occurred in the area of the earthquake epicenters. So areas in red became lower, areas in blue became a little bit higher just from the movement of these earthquakes. The 7 inches might not sound like a lot of change, but if you have a home or a business that is on a low, broad coastline, 7 inches is a lot. So these photos are of a near shore area on the south coast of Puerto Rico. These are areas that, as you might guess, were previously on dry sand and reasonably far away from the actual shoreline. And now they are shallowly submerged in the ocean. This video, which is another shakeout video, will give you an idea of what to do if you are in an earthquake while on the shore.
Great Shakeout earthquake drills encourage you to practice how to protect yourself during an earthquake. Let's learn what to do when you're near the shore. Along the shore of the ocean, you are at risk for a tsunami. Tsunamis are most often created by large undersea earthquakes or landslides that shift the water up or down, sending out waves in all directions. When these earthquakes are far away, there can be several hours before waves arrive. But when large earthquakes happen just offshore of your location, waves may arrive in a few minutes. In this situation, there are natural warning signs of a potential tsunami. One such sign is feeling strong earthquake shaking near the shore. Whether you are at the beach or in a building, immediately drop down onto your hands and knees. An earthquake is less likely to knock you over in this position, and you are a smaller target for anything falling or flying. Then, cover your head with your arms, clasp your hands around your neck, bend over to protect your vital organs. Finally, hold on. Remain on your knees, close your eyes and mouth to protect against dust and debris. Remain in this position until the shaking stops. Other natural warning signs of an imminent tsunami are seeing the ocean rise or fall, and usually far, or hearing a loud roar from the ocean. So whether you feel strong shaking or observe these other signs, immediately evacuate as a tsunami may be on its way. If you are in a designated tsunami zone, follow evacuation signs to a safe place. If there are no signs, get to high ground or inland, away from the water, as far as possible. Walk quickly rather than drive to avoid traffic, debris, and other hazards. You might also be safe going to a high floor of a sturdy structure. Unlike a tsunami from a nearby earthquake, a tsunami created by a distant earthquake may not arrive for several hours. It's important to know the first wave is usually not the largest and most dangerous. The danger can last for hours, sometimes days. In this situation, the National Weather Service will issue warnings that are transmitted from your local emergency management department, tsunami sirens, broadcast media, and weather radios. If you receive a tsunami warning and are near the shore, follow the directions of emergency officials. If ordered to evacuate, take your emergency kit and get to high ground or inland away from the water, as far as possible. Once you reach a safe place, stay there. A tsunami is a series of waves, and the first one is not always the largest. Ocean currents can be dangerously strong, especially in harbors and coastal rivers. Do not leave your evacuation area until you hear from officials that it is safe. Learn more about tsunamis and register your tsunami preparedness activities at tsunamizone.org. Visit shakeout.org to practice earthquake safety with millions of people worldwide and to see videos showing what to do in a variety of situations. Great Shakeout.
In closing, I want to show you how the waves of the January 7th earthquake rippled across the continental United States. We didn't feel that earthquake in Kansas, but the US array of seismographs absolutely did. Thanks for listening, everyone.